In the last section, we established a high-level information model for episodic memory that allowed us to understand the phenomena in terms of concepts we can use at a deeper level. Now, the high-level model is approximate, but it makes it clear how the information models support the phenomena. And in fact, most of our thinking about cognitive tasks can be carried out at this higher level, provided we're confident we know how to map to more precise models if we needed to. So, to confirm we can confidently use these higher level models, let's have a look at a range of deeper levels to get more precision in terms of anatomy and physiology. As a first step in this direction, it will be very expensive in connectivity resources to have every individual column directly connected to every other individual column that ever expanded its receptive field at the same time. But the hippocampal system already contains columns with receptive fields that are groups of columns elsewhere in the cortex that expanded their receptive fields at the same time in the past. These hippocampal system receptive fields are established to support change management, so with some qualifications, these resources can be used for retrievals of episodic memories. There are lots of receptive fields in the hippocampal system that correspond with groups of cortical columns that change their receptive fields at the same time. Fields like this are located in the parahippocampal and the perirhinal cortices, in the entorhinal cortex, in the CA fields, and even in the dentate gyrus. But there are a couple of issues with using these receptive fields to drive indirect activations. One key issue is that the outputs from the hippocampal system drive receptive field expansions. And if the same outputs were used to drive indirect activations, there would be all sorts of unnecessary receptive field expansions whenever a memory was recalled. In other words, if the neurons driving indirect activations are the same as those that in other circumstances drive receptive field expansions, the connectivity is always in place, and the obvious question is, why would such expansions not occur even if, in the indirect activation situation, they're inappropriate? The second issue is that to recall a good memory of an earlier event, it would be better to indirectly activate all the receptive fields that were active during that event, not just those that expanded their receptive fields. In other words, although managing receptive field expansions needs hippocampal system receptive fields corresponding with groups of columns that expanded at the same time in the past, for episodic memory retrieval, it would be better to have receptive fields defined by groups of columns that were active during past receptive field expansion episodes, not just those that expanded. Receptive field expansions are driven from CA1 through the subicular complex to the entorhinal cortex and then on to the other cortical areas. And CA1 only has one population of pyramidal neurons, one layer. So since it's the primary driver for receptive field expansions, there will be difficulties if it was involved in indirect activations. And in fact, it's found that hippocampal damage limited just to CA1 can eliminate the ability to create new declarative memories, but seems to have no effect on past episodic memories. On the other hand, the associated cortical areas have more complex neuron arrangements, perhaps with room for separate populations of pyramidal neurons supporting the two functions. Cortical columns able to discriminate between different types of groups of objects are probably located in the parietal cortex, and the parietal cortex is interconnected with the parahippocampal cortex. So it's in this interface between the parietal and the parahippocampal cortices that we should look for different neuron populations to support the two functions. But before we look for these separate neuron populations in detail and look at the connectivity needed, let's have a look at the connectivity required to support the appropriate indirect activations at the column level. As I said, parietal columns are interconnected with the parahippocampal cortex, and parahippocampal cortex is of course part of the hippocampal system. In the parahippocampal cortex, there are receptive fields that correspond with groups of parietal columns that have expanded their receptive fields at similar times in the past. For the moment, let's assume we can also use these fields for indirect activation and see how the process could work. Outputs from the parietal cortex are available to the parahippocampal cortex, and a receptive field in the parahippocampal cortex is defined by a group of parietal cortex columns. Then there's also some provisional connectivity that I've indicated by dotted lines. This provisional connectivity is implemented by silent synapses with zero synaptic weight. These synapses can acquire weight if they're receiving inputs just before their neuron fires. Different parahippocampal receptive fields are defined by different groups of parietal columns, and in each case, a receptive field also includes provisional inputs. So, for this simple model, let's specify some conceptual parameters. For the area in the parietal cortex that discriminates between different types of groups of objects, let's suppose that at least 8 columns must detect their receptive fields in every experience. And assume that one parahippocampal column will detect its receptive field if 4 or more of the parietal columns providing inputs to its receptive field are active. And in the parahippocampal cortex, at least 4 columns must detect their receptive fields in response to any experience. So let's use this conceptual model to understand the processing of an experience that has very little novelty. In the parietal area that discriminates between different types of groups of objects, the minimum number of columns is already detecting receptive fields, so there's no need for receptive field expansions. Outputs from these columns go to the parahippocampal cortex, resulting in column receptive field detections that again meet the required minimum, so again no receptive field expansions occur. Now consider a more novel experience. Because of the novelty, the number of receptive field detections at the discriminates groups of objects level doesn't reach the minimum. When the outputs are communicated to the parahippocampal cortex, again the number of detections doesn't meet the minimum. However, there are several parahippocampal columns that have inputs just below the threshold for receptive field detection. In other words, they have strong internal activity. And this information is communicated through the entorhinal cortex up to the hippocampus proper. And let's suppose that the 2 columns I've indicated by the green arrows, out of the 3 with strong internal activity, are selected for receptive field expansion, which means that they get strong inputs back from the entorhinal cortex. These 2 will fire, and their activation will result in receptive field expansion, as we'll see in a moment. Let's suppose further that there are 3 columns in the discriminates groups of objects area that are inactive but have strong internal activity. The requirement is that just 2 fields expand to reach the minimum number. Now, a parahippocampal column projects back to the parietal columns that define its receptive field. So if we look at the parietal columns that contribute to the receptive fields of the active columns in the parahippocampal cortex, the currently active parietal columns obviously feature fairly often. But sometimes parietal columns with no output but strong internal activity could also feature. So, focusing for example on this column circled in green, it forms part of the receptive field of the parahippocampal column indicated by the purple arrow. So there will be connectivity back from that parahippocampal column to the cortical column. Similarly, the same parietal column forms part of the receptive field of this second active parahippocampal column, indicated again in purple arrow, and will therefore receive a projection back from that column. So that parietal column indicated by the green arrow will get substantial input from the active parahippocampal columns. And I've indicated the degree of, conceptually, the degree of input by the width, the line width of the arrow, the green arrow. The second parietal column with strong internal activity also forms part of the receptive fields of two of the active parahippocampal columns. So again, it'll get substantial input back. But the third parietal column, although it has strong internal activity, only forms part of the receptive field of one of the active parahippocampal columns. So it'll get rather less input back from the parahippocampal cortex, as indicated by the somewhat thinner green arrow. So what will happen is that only the two columns that get strong input back from the parahippocampal cortex will be activated, and therefore have their receptive fields expanded. The outputs from these newly expanded columns are then available as inputs to the parahippocampal cortex, and any silent synapses they have onto active parahippocampal columns will gain weight. So they'll be added long-term to the receptive fields of those parahippocampal columns. So this is the final result in the novel situation. The minimum numbers of receptive field detections are achieved, both in the parietal and the parahippocampal cortices, by means of appropriate receptive field expansions. So let's record that pattern of parietal column activation during the original experience at the top, and think about how a recall process could occur. A recall process is initiated by hearing words that relate to the earlier event, leading to indirect activation of a set of columns in the parietal cortex by the semantic memory mechanisms. And if the words have been chosen appropriately, there will be a small degree of overlap between these columns and those active during the earlier experience, but not enough overlap to have sufficient recommendation strength to describe the experience. If recommendations to activate on the basis of past simultaneous expansion are accepted, outputs from the parietal cortex are released to the parahippocampal cortex. And the columns in the parahippocampal cortex will get varying degrees of input, and the numbers indicate the number of parietal columns providing input to each parahippocampal column in this simple model. So let's suppose that if indirect activation behavior has been accepted, the parahippocampal columns with the largest numbers of inputs will fire. Extinguish the activity of the seed population and see what happens as a result of activation of those parahippocampal columns. Remember, there's reverse connectivity from the active parahippocampal columns back into the parietal cortex. So each of the active parahippocampal columns provides inputs back to some of the parietal columns. And if you add up all the inputs, you see that the parietal columns coloured dark red get a lot of input, and the columns coloured pink get some, but less input. And you can also see that the parietal columns with strong input tend to have more overlap with the columns in the original experience than the seed columns that were activated by the words. So given an appropriate seed population, using indirect activation based on the information recorded in the hippocampal system can result in convergence on an active column population similar to the original population. However, at this somewhat more detailed level of description, the issues I mentioned earlier, that neurons driving indirect activation can't be the same as those that drive receptive field expansions, and the need to indirectly activate all the columns active during past periods of receptive field expansion, not just the ones that expanded, these two issues aren't addressed. To understand how these issues can be addressed, we need to move down to an even more detailed neuron level of description. I will do that in the next section.